So let's have a look at how you do this. So the following is known as Knutson's theorem, and what he did is he applied two fundamental conservation principles to positive esters. And Knutson used the following two principles. One is he assumed that the total water volume of the estuary is constant, okay, on average. He also postulated that the total salt mass of an estuary is constant on average. And when I say on average, I'm not talking about the tidal in and outflows, the tidal oscillations that you have. I mean on average. Okay? If you average over a tidal. And these two principles can be expressed by equations. And these equations can be used to calculate flushing time. Okay, so how do you calculate that in terms of volume? Okay, volume conservation is a fundamental principle for incompressible fluids. Fluids that you can't compress, the volume has to stay the same. And in this system of estuaries where you have three connections or three openings, you have to work out that the sum of all volume inflows and outflows has to be balanced. Everything that comes in has to go out. Okay? And you have two sources of inflows of volume. One is the fresh water coming from your river. The other one is the seawater, the salt water coming from the adjacent ocean. These two here showing the errors. And the inflows have to be balanced by the outflow, which is that of diluted seawater. Okay? There might be some small corrections that come from surface freshwater fluxes. You know, if you have precipitation, evaporation changes the volume. Okay, and in principle, you can work that out if you know what the transverse velocity is in terms of the speed. Okay, the volume transport is the speed that you have times the volume of your the area of your transect. Okay, the area times the speed gives you the volume. Salt mass you can work out if you know what the volume transport is times the salinity times the density gives you the amount of salt in kilograms per second that is moved in and out or out of your estuary. Okay, and you can use these equations. Let's see how that works now. Here are the equations. So what we use to work out these equations is we use an index 0 if it's the river water, it's shown here. The outflow has the index 1, and the inflow from the ocean has the index 2. And then you can work out these equations, and we're not going too much into the details. They're written down here. Volume conservation implies I switch on the pointer, means that the inflows and outflows have to be balanced. Okay, and salt mass conservation, actually there is one term dropping because there's no salt coming from the river. So you also have a balance in terms of for the upper and lower layer. Okay, there's only one assumption for simplicity. We just treat the density all the same, you know, because it's not too different. The density of seawater compared with that of fresh water is, you know, it's about a 1% difference. So there is not a big change, 1 to 2%. Yeah. And now you have two equations. You have a number of unknowns, and you can manipulate these equations, rearrange them. And now let's see what you get. What you get is actually you can work out what is the outflow Q1. Okay, you can work that out. It's the same as R, it's the input that comes from the river, times salinity values. S2 divided by this delta S is the difference between bottom layer and top layer salinity. Oh, this is cool, huh? This is cool. So if you know what the R is, the input of fresh water into your estuary, you can work out the outflow volume transport from measurements of salinities. Similarly, for the bottom layer, you can do that. You can also work it out from these equations, and you can get a formula. The difference is here that you have a minus because the direction is up. You have an inflow of seawater, okay? And so anyway, so what you can see here now is that you get an estimate of what is the Q2. And the Q2 is what you use in your flushing time. So what you need to plug in is your result from these equations, and you have a flushing time formula, and we do that on the next formula. So this is what you can use for highly stratified estuaries, but also for other types of, or slightly stratified. Okay, so now plugging all the numbers in, you can work out your flushing time, TF, is the volume of your entire estuary divided by R. This is the volume influx, the volume transport of fresh water into your system, times, and then in brackets 1 minus the surface salinity divided by the ocean salinity. Okay, because the ocean salinity is what you, seawater salinity is what you find in the bottom layer of it. And this is pretty cool. So although you have complex tides, so you can, the average flushing time you can work out from salinity. This is amazing, isn't it? Okay, and this is known as Knutson's formula, work out flushing time. And in fact, if you think about it, this formula, if you use the full form of this formula, you can actually calculate the flushing time at any transect, at any section. In the middle, it works in the middle, or at any location it actually works. You can derive two-dimensional, at least, flushing times for your positive estuary. All right, and I want to show you one last simple estuaries that a simple estimate of flushing times that's often used for slightly stratified.